Hello, I'm David Forster from Gold Standard Maths. Today's work solution is from a Further Pure 1 paper set by Edexcel in 2023, and the topic is conic sections, properties of ellipses. This question requires us to use the standard properties of an ellipse, and these are listed in the formula book. So I suggest when you try these questions, you find the page in the formula book, which looks like this. Have it open before you, so even when you think you know the formulas, you can double check that you've got them right. It's very easy in an exam to get a plus or minus in the wrong place and to mess up in that way. So have the page open. The question is like this. It requires use of these formulas. The ellipse E has equation x squared over 16 add y squared over 9 equals 1, and part A is to determine the exact value of the eccentricity of E. So we're going to use the formula for eccentricity of an ellipse. The words to note here are determine. Determine is slightly stronger than find. It means that some method must be apparent, and exact value means what it says. If it's a surd, we leave it as a surd. So the formula we require is the formula here, b squared equals a squared 1 take e squared. So we use b squared is 9, a squared is 16. Rearrange, we get it, e squared is 7 over 16, so e is root 7 over 4. We want the answer to be exact and simplified, which it is, and e is a positive number, so only the positive root. Giving plus or minus here is likely to lose you marks. So part B of the question. Now it is asking us, we've got points P and Q, which are given in parametric form, cos theta and sine theta. L1 is the normal to E at the point P, and we're being asked to use calculus to show that L1 has the equation as given, which has got x and y in it and the parameter theta. So, sketching a diagram for this, there's our ellipse with the semi-axes 4 and 3. Those are A and B respectively. P is the point A cos theta, 4 cos theta, and y of P is 3 sine theta. For Q, it's a negative y value. So if we just check back to the question, we've got for x 4 cos theta, 3 sine theta, and for Q, 4 cos theta minus 3 sine theta. Theta is in the first quadrant. We are told that line L1 is the normal to the ellipse at P. So finding normals to conic sections at given points is a standard requirement. We're going to need to find the gradient of the ellipse at point P, and since this is a show that question, we're going to show the workings clearly. We can do this either differentiating implicitly or parametrically. Given the answer has got the parameter in it, I suggest parametrically is the more obvious way to do it. So dy dx equals dy d theta divided by dx d theta. Differentiating y and x with respect to theta gives us 3 cos theta over minus 4 sine theta. Now we are looking here for the normal, not the tangent. So we've got to do the negative reciprocal of the gradient, which will be 4 sine theta divided by 3 cos theta. The other thing we know about L1 is the point it goes through, which is P. So using our standard formula for a straight line, y take 3 sine theta equals 4 sine theta over 3 cos theta times x take 4 cos theta. Let's simplify. Multiply by 3 cos theta both sides. collect the 4x sine theta, take 3y cos theta to one side, and the 7 sine theta cos theta to the other side, and we've got the formula as required for line L1. Just another reminder, the word show means that full clear work is needed. Just to show you the alternative way of finding dy dx using implicit differentiation. Obviously in an exam you only need one method, but here's a good alternative to know. We differentiate implicitly with respect to x, giving us 2x over 16, add 2y over 9 dy dx equals 0. Rearrange to find dy dx equals minus 9x over 16y, and at the point P, we put in the x and y values, which are 4 cos theta and 3 sine theta, giving us the same answer for the gradient, minus 3 cos theta over 4 sine theta. That method is perfectly valid. It seems to me that given that we want the answer in terms of theta, the parameter, that parametric differentiation is the more obvious thing to use. Part C of the question. A line L2 passes through the origin and point Q. The two lines intersect at point R. Determine in simplest form the coordinates of R. So this time the answer is not given. It's a determine question. It wants the answer in simplest form, and it wants coordinates, so that is x and y. The first thing we will need is the equation of L2, and looking at my sketch, L2 goes through Q and the origin. So we need the gradient of the line L2 and a point it goes through. So the gradient of L2, it goes through point Q, so the gradient is going to be minus 3 sine theta over 4 cos theta, minus 3 sine theta over 4 cos theta. A point it goes through, you can use either naught or Q. It makes sense to use naught naught, makes it a lot simpler. So when the lines meet, I'm taking the equation of L1 and replacing the y value by the equation L2. So L2 is y equals minus 3/4 sine theta over cos theta x. I'm taking that and putting it in instead of y. And I now need to rearrange to find x and then to find y. Sine theta can be cancelled everywhere. Sine theta is not naught at the point that they meet. It's not on the x-axis. So we get 4x, add 9/4 x equals 7 cos x, giving us x equals 28 over 25 cos theta. And working out y using the equation of L2, we get minus 21 over 25 sine theta. We want the coordinates, so I've written that in coordinate form with brackets and comma, and that is the simplest form. Part D of the question requires us to use the answer to part C, so if you've not got that correct, you haven't got much hope on part D. It is a hence question. Show that as theta varies, R also lies on an ellipse with the same eccentricity as ellipse E. So looking at our diagram, we're allowing point P to go around the ellipse. Point R is where the two lines meet, and that is also going to describe an ellipse. We want to prove that, and we want to prove it's got the same eccentricity. That doesn't mean it's got the same size, but it does fit the same formula for eccentricity. So let's look at the coordinates for R that we've just found. We found x equals 28 over 25 cos theta, and y equals minus 21 over 25 sine theta. Compare that to the parametric equations of an ellipse. We go back to the formula sheet and we see for an ellipse the parametric form is a cos theta, b sine theta. So compare that to the coordinates of r, and we're going to find that is of the form of an ellipse, with a is 28 over 25 and b is minus 21 over 25. Do make sure you state clearly that we have shown this is an ellipse. Using again the formula for eccentricity with these a and b values and rearranging, we get e squared equals 7 over 16, which is the same as for the original ellipse, e equals root 7 over 4. So we have shown it's an ellipse and we've found the eccentricity. So make sure we do state it's an ellipse. Part D is dependent on part C. You could also do part D. Instead of using the parametric equations, you could eliminate theta. We know sine squared theta and cos squared theta equals 1. Rearranging the equations of r, that will give us 25y over minus 21 squared, add 25x over 28 squared equals 1, which changes into the Cartesian equation of an ellipse, once again with a squared being 28 over 25 squared and b squared being 21 over 25 squared, which is again an ellipse. So a nice question using the properties of an ellipse and the formulas given in the formula book. A fairly standard question. It's worth spending time studying these questions because very much they are of a similar type in the exam. So that's it for today. I'm David Forster. This is Gold Standard Maths. See you next time.